Okay, good morning, everyone. Let's start the last lecture. Today we'll continue from Tuesday, where we stop here. We talk about what is the singular value decomposition to a matrix, and then I briefly mentioned this theorem, which says if you have a matrix A, m by n matrix, if you with some rank R, if you give me a singular value decomposition like U sigma V, the transpose like that, then this theorem tells us quite a lot of information about this U sigma and V. Actually, we don't need to. We will not prove this theorem here. The proof to these items it's an exercise in the problem set. You can try to prove them. Yeah, and also here is a remark. Just say one simple consequence of this theorem is that if A has a SVD like this, A equal to U sigma V transpose, then the rank of A is equal to the rank of sigma, which is quite obvious because the rank of A is just R, and how we construct sigma, how we construct sigma is here. It's the first item. You just say the non-zero entries of sigma is just this non-zero singular, this are non-zero singular values of this A. So of course, they have the sigma and A, they have the same rank. Yeah. Okay, so then the next theorem says that every matrix has a singular value decomposition. Okay, so we will not prove this one here. The proof is also is in the MTH 2025 workshop. Okay, so but this theorem is super useful. We just know now for sure every matrix has a singular value decomposition, and later on we will I propose an algorithm to find a singular value decomposition for matrix. Okay, so before we do that, let's first talk about one more theorem. This is the last theorem we will talk about this semester. So this theorem says we have a T. T is a linear transformation from Rn to Rm, like transform a n-dimensional vector to an m-dimensional vector. And T act on some x is just equal to A times x. Okay. And here A is a m by n matrix, let's say. And let A have a singular value decomposition like that. Okay. So then if B is the set of columns of V and B prime is the set of columns of U, then this is true. Let me write. This is true. So what's the left-hand side? That is the matrix for this linear operator relative to these two bases. You can find the definition of this. If you don't remember, this is in the definition of 5.4.102. Yeah, it's in chapter 5. I talk about the matrix representation. So anyway, and let me write down what's this. So TB prime B, this means this is a matrix, and the columns is, for example, the first column is T. Let me introduce a bit more notation maybe. Yeah, I have enough space, so I'll just do it here. So let's write So B is a set of columns of V, right? So let's just write B as it's a set of columns of V. Let's just write the columns of V as V1, V2, and to V what? So V is maybe I should start from here. A, what is A? A is a m by n matrix. So U is a m by m matrix. Of course, sigma is a n by n matrix, and V is a n by n matrix. Okay, seems a bit confusing. So, yeah, nice. So B is a set of column vectors of V. So just from Vn. It's not a Vm. I just want to make sure there's n columns of V. Okay. And B prime is a set of columns of U. So let me just write U1, U2. This U is for the columns of U, M, because we know big U is a m by m matrix. Okay, that's good. Now, what's this TB prime B? That's just a matrix with columns like this. The first column is a B act on V1, and what's the coordinate on this vector in the basis of B, or B prime, sorry. You just say the coordinate of this T times V1, T act on V1, using the basis of B prime. I will explain earlier later explicitly what's this. So the second column is T act on V2, tutor on B prime, and the last one is TVN on B prime. Okay. Yeah. So we want to show this matrix is just sigma. This matrix is just sigma. That's what we want to prove. Okay. Let's try to prove it. Let's just start the one of this T. Let's study T V I. Tutor. Yeah. Okay. So T of Vi, Vi is the ith column of V, so this is equal to A times Vi, right? Because we know T act on X is equal to A times X. Yeah, and that's defined here. So we have this, and then of course A. Now we should use the SVD of A, which is U sigma V transpose V, the ith column of V. Okay, so then this is equal to, let's just call, because we want to write TVI using the basis of U. Now we already have U here, right? The big U here. So let's just call this thing Ci. It's a vector, of course. So it is equal to UCI. Okay. Yeah. Yeah. As you can see, what is the Ci? Ci is because big sigma is m times mn. Yeah, and V transpose is what? V transpose is n times n, and Vi is of course is n times 1. So in total, this C is a m by 1. So it's a column vector with a number of rows is m. Okay, so that's C. So now C is the column vector. So now we can write this as, so this is a U times, U is a matrix, m by m matrix, then multiplied by this column vector. So we can write down this as ui, ith column. Should I say ui? Maybe no ui. uk. Yeah, ci sum over all k from 1 to m. Yeah, so here u is the uk is the kth column of should I say yeah, maybe I shouldn't say that. I should say CIK. Yeah, that's more because I is a CI is a column vector. So U times CI is just the UK is a column vector times CI the case rule. Yeah, equal to that. Okay, so from here we can see what is TVI if we use the basis of B prime. The basis of B prime is this basis B prime. Basis B prime is the set of column vectors of U. So now from here, you can see we already express TVI using this UI, right? So actually, this is just CI. Okay, yeah. So this column vector CI is just the coordinate of TVI if we use B prime as a basis. Yeah. So use basis. Maybe I should write one more step. It just means that TVI using basis B prime, we want to know the coordinate of using basis B prime. So we want write everything. Let's say 1 times U1 plus CI2 U2 M or CI the M's rho UM. Yeah, so now we write the TVI using basis of B prime, which is U1, U2 up to UM. So the coordinate, of course, is just this C in front. Okay. Yeah. So we have this. Okay, so now we are very close. So we want to prove is T B prime B is a sigma. So now we just want to show. So this is ith column. This is the ith column of this TV of this TB prime B. That's the ith column, right? So we want to show this is the ith column of sigma. Now we are done. Okay. So now what is CI? CI is as we defined here. CI is just sigma times V transpose VI. Okay, so indeed we have sigma here, which is good. So now this is equal to sigma VI transpose V transpose. We just apply transpose. It's slightly easier for the calculations. Right, so yeah, this part is equal to that part. We just use the property of transpose. Yeah, and what's inside the transpose? Okay, now VI is a column vector. If I transpose, now it's a row vector. The row vector multiplied by a matrix. So we can write this as. So now eventually we'll have a row vector, and in this row vector, the entries will be VI transpose times V1. That's the first element. None is a number. First element in this row vector. Then Vi transpose. Vi. V2. That's the second element. And Vi transpose. Vn. Yeah. Now what's this? Because we have SVD, so U and V, they are orthogonal matrices, and the columns of them form orthonormal bases. Okay, so because they are orthonormal bases, so what's this? So for this row vector, only one entry is non-zero, and that non-zero entry is just 1. And this 1 happens at the ith entry, where we have Vi transpose times Vi. That one is 1. And then maybe somewhere here, let's say ith entry. Yeah, and all others just 0. Okay, so of course this is just EI. Or you can say transpose, because EI means a unit vector, a column vector, we transpose is a row vector. So this is just a unit vector. Okay? Yeah, so that's just EIT. And then what is CI? We continue from here. Okay? Continue from here. So now CI is just sigma times EIT, which is just sigma times EI. Okay. So what's sigma times EI? Sigma is a matrix. EI is a column vector. And ith entry is non-zero. So sigma times EI, we just extract the ith column of sigma. So just the ith column of sigma. So what did I just say? Or you can say ith column sigma just sigma ith column. Yeah, I use this. I don't know, maybe not good notation. Fix what is little sigma. Let me just say ith column of sigma. Okay, so that's this CI. So now we know. Then we from here. So we know this TVI B prime is equal to the ith column of sigma. Yeah, and we know this TVI B prime. That's the ith column. That's the ith column of the matrix we want. Okay, so now it just follows. TVI B prime B, this matrix is just sigma because they have the same columns. Yeah. Okay, yeah, that's the proof. Yeah, you just say we have a SVD, then we have two bases. One is the two orthonormal bases. One is the column vectors of U. One is the column vectors of V. And if we define a linear operation like that, Tx equal to Ax, then the matrix of T relative to these two bases, B prime B, just this diagonal M by N matrix, sigma. Yeah. Okay, then let's move to maybe the most important thing for today. Is that how we giving a matrix, how we find the SVD. Hopefully everyone after this lecture will know how to do that because it is super important. It's definitely accessible. So just make sure you know how to do this SVD for a matrix. So you say from a previous theorem, we know that for any matrix, there exists SVD, and this algorithm tells us how to find that. So if we have an m by n matrix A, so we first find the eigenvalues of this, not A, okay? We first write down A transpose times A, which is a symmetric matrix. A may not be symmetric, but A transpose times A is symmetric. So we first write down this A transpose times A. Then we find the eigenvalues and the corresponding orthonormal set of eigenvectors. Yeah, and then we order them like lambda 1 is the largest eigenvalues, and lambda 1 up to lambda r. This is the r positive eigenvalues of A transpose A. Then the rest of it, if r is still less than n, then the rest of it, the eigenvalues just 0. The rest of it is 0. Okay, so we have r positive eigenvalues and maybe some 0 eigenvalues. Yeah, and then we and this vi is the eigenvectors, also normal eigenvectors, not just eigenvectors, also normal eigenvectors, and then we put them together, we obtain v. Okay, we have v. And then we know these positive eigenvalues. We take the square root. We take the square root of these positive eigenvalues, and we call this sigma I for I equal from 1 to r. Right? We have r positive lambdas. So then this is the non-zero diagonal entries of sigma. The rest of entries are just 0. Okay. So now we know sigma, we know v. Now next we just need to know u, then we are done. Okay. So u in 2 steps. So for I from 1 to r, for these r columns of u, that's easy. We just use this. So it's just like a multiply ui of vi divided by sigma I. Yeah, that's ui. Now, so for each column vector of vi, but this I has to be one of the first r columns. Then so we have r columns of u. Right? Now from here we know the first r columns of u. But in some case, this little r, for u is a m by m matrix, right? Sometimes the r is less than, sometimes r is less than m. But if r is less than m, which means we find the first r columns, we still need to find the rest of it, the rest few columns. So that is, we want to find ur plus 1 up to um, and they are the orthonormal basis for the known space of A transpose, which is just, so which means you need to find, so you need to find the, here we know A is just our matrix, and you take the transpose, and using this like Gaussian elimination and back substitution, you can find the orthonormal basis for the known space of A transpose. So that then you will get this ur plus 1 to um, the rest columns of u. Okay, so then you get the 4u. And in some examples, little r just equal to m, which is very nice. Then you don't need that, because if little r just equal to m, by this step, you already find all columns of u. But in some case, you need to study the known space of A transpose to find the rest of U if R is less than M. Okay, just be careful about that. Yeah, this is the 5 steps. Now let's do an example. So you don't need to worry about this too. Okay, let me write down all steps for this example. Yeah. So find a singular value decomposition of this 2 by 3 matrix. I like to write down the dimension just make sure I know the columns and the rows. It's 2 by 3. Okay, so how to do that? The first thing to do is to write down A transpose A. So with A transpose, that is easy, right? Just 1, 1, 0, 0, 0, 1, 3 by 2 matrix. Multiply by 1, 1, 0, 0, 0, 1, 2 by 3. So in total, we have a 3 by 3 symmetric matrix. So we can quickly calculate with this. This is 1, 1, 0, this is 1, 1, 0, and 0, 0, 1. Okay, yeah. Yeah, okay, now next is to find the eigenvalues and eigenvectors of this. Okay, to find the eigenvalues, we study the determinant of this, right? Determinant of this. So this will be determinant of, what's this? This is lambda I is the identity matrix. So this we will have lambda minus 1, lambda minus 1, lambda minus 1 for the diagonals. And this will be negative 1, negative 1, 0, 0, 0, 0. Yep. Okay. Of course, we want to how to find the determinant of this 3 by 3 matrix. It's easy to start with this entry because that's the only non-zero entry in its column and row. So it's just is equal to lambda minus 1. This value times the determinant of lambda, the rest of the matrix, which is that. Okay, now it's a 2 by 2 matrix determinant. Determinant is easy to calculate. This is lambda minus 1, lambda minus 1 square minus 1. Okay, so it will be lambda minus 1, lambda minus 2 times lambda. Yeah. Yeah. This is just equal to that. Yeah. That's it. Yeah. Okay. Yeah, so now we can read, after we factorize this, we can directly read the eigenvalues of A transpose A. So the first one is 1. Let's order it, just in case we make some mistakes later, so we order it. So 2. Largest one, second largest one, lambda 2, it's a 1, lambda 3 is 0. Yeah. So you can see from here, we can see what is our R value, the rank of A, which is 2. Yeah. Because R means the number of non-zero eigenvalues. Okay, so we find that. So sigma 1, which is the singular value of A, is also easy. That's the square root of this eigenvalues. So we also write them down. Yeah, and then that's will be the maybe most technical part. Find the orthonormal basis. So the orthonormal basis corresponding to we need to find this for each eigenvalues. Let's start with the first eigenvalue, the largest one. What's the orthonormal basis for the eigenspace with this eigenvalue. So that is just the known space of 2I minus that. Right, that's just a known space of that because we put lambda to be 2. Yeah. So which is the known space of, now if we put lambda to be 2, so what is just, this is 1. So we're starting from here by putting lambda to be 2. It's 1, 1, 1, negative 1, 0, 0, negative 1, 0, 0. Yeah. Okay. So now we need to do some so this, from here it's not very clear what the basis is, but we can do the, what's it called, Gaussian elimination. So this is similar, row similar to another matrix. Yeah, actually this is very easy because if you see, if I plus the second row by the first row, first row is the 1 minus 1, 0. Yeah, if I second row plus the first row, that's what my new second row, that will be 0, 0, 0. Okay, which is good. So it's the third row is just keep it. Okay, so now it's this is simple enough. We can just use back substitution to find the basis. So what's the basis? So this is, so the known space is span. You can say it's a span by its basis. So what's its basis? Its basis is actually, so so everyone know how to do this back substitution to find the basis. So we start with the third row. In third row, it's the third. We have a 1 here. So which means if we want to find the basis, that one should be 0, right? Because it is 1 there. So this third element has to be 0. And the second row is all 0, which means for this vector, the here can be anything. So 1 can be anything, you just put 1 there because the constant does not matter, just put 1 here. Yeah, and from the first row is 1 minus 1, so which means the first 2 entries in this vector, they are equal. Yeah, because so it's just minus 1. Yeah, or equivalently, you can say 1 minus 1, 0. Does not matter. Yeah. So this is using the back substitution. Hopefully everyone knows how to do that. Yeah. So yeah. Yeah, but let's use this one. So from this, the information we need to know is just that the basis for this basis column vector, the last entry has to be 0. The first 2 entry, first 2 entry they are equal. First 2 entry they are equal. The third entry has to be 0. That's it. So it's just 1, 1, 0. If you put a minus 1, 0, that's also okay. Yeah. 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 So we find the basis. This is the basis, not also normal basis. It's the basis corresponding to the lambda 1. So we should know V1 because V1 is but V1 is the also normal basis for the space, eigenspace corresponding to a lambda 1. So we need to normalize it to make it also normal basis. Yeah, so we find the V1. Yeah, then let's continue to the lambda equal to 1. So then we need to study the I minus A transpose A, the known space of this. Okay, now because I put lambda to be 1. So this is a known space of, here if I put lambda to be 1, that would be 0, 0, 0, negative 1, 0, -1, 0, 0, 0. Yes, yeah. Actually, this is already quite simple. We can just directly use the back substitution. Again, the third row is all 0, so which means the third element can be anything. So we just put it to be 1. And the second row is -1, 0, 0. So which means we have a -1 here. So which means but it's in the first column. So which means it has to be 0. Yeah. And the first row is 0, -1, 0. So which means the second element is also 0. Yeah. So that's a spell of that. Is that correct? Yeah, I think that's correct. Yeah. Yeah, we are lucky because the vector we write here is already a unit vector, so we don't need to normalize it. So V2 just directly this. Okay. So now we have V1, V2, now V3. V3 is the basis for corresponding to lambda equal to for the eigenspace corresponding to lambda 3, which is 0. So just here is a negative, just a negative A transpose A. But we will study space, and the constant negative does not really matter. You can keep it, but it does not matter. So this will be the known space of what's the transpose? Yeah, 1, 1, 0, 1, 1, 0, 0, 0, 1. Okay. So yeah, by doing the this matrix is row similar to what? You can see the first two rows, they are the same, so you can get rid of one of them. 0, 0, 0, 0, 0, 1. And by back substitution, so yeah, because the third row we have a 1 here, so we know the third element has to be 0. Second row is all 0, so can be anything. Put a 1 here. And the first row, which means they are the first two entries, the sum of them has to be 0. Yeah, I like to start with positive, so let's just change it order. 1 minus 1, does not matter. Yeah, you can put a -1, 1, 0, or 1 minus 1, 0, does not matter. So yeah, this is the basis, but again, now this one is not orthonormal. Let's make it orthonormal and call this V3. Yep. Okay, so now we know our V. So V is just V1, V2, V3. Okay. We know V, and we also know sigma, right? Sigma, because we know here. This is and two non-zero, two positive values, sigma 1, sigma 2. They are the diagonal non-zero diagonal entries. So root 2, 1. Root 2, 1. All others are 0. So remember, sigma is the dimension of sigma is the same as the A. A is m times n, so sigma is also m times m by n. So it's yeah. So we know it's two non-zero or two positive entries. They are root 2, and 1. Okay. So next we just need to find the u. So U1, so in our case, we know R is equal to 2, it's the rank, right? Because lambda 1, lambda 2, they are positive, lambda 3 are 0, so R is 2. So at least we can find U1 and U2. So what is U1? U1 is A times V1 divided by sigma 1. And we know A, I don't quite remember. A, what is A? 110,001. And what is our V1? V1 is just root 2. V1 is here, 110. What is our sigma 1? Root 2. Yeah, root 2, they put together, half. So this matrix will be 112, 0, which is super easy. Which is 1, 0, U1. So we find U1, okay? And then we do the similar thing to find U2. So what is sigma 2? Sigma 2 is just 1, that's easy. And A is still 110,001. And what is V2? V2 here, 001. Yeah. So then this is just what? 0, 1. Okay. Yeah. So U1 and U2 we have here are just super nice. Also normal basis for R2. 1, 0, 0, 1. Do we need to find U3? Yeah. No. Yeah, that's good. Because U is a m by m matrix, and m shouldn't say that. It's a m by m, which is a 2 by 2 matrix. Yeah. So all you can say that rank R is already equal to 2, which is equal to the number of rows of A. So that's enough. So we don't need to. There are no more column vectors for U. Yeah, so U is just this U1, U2. We put these two right here. Okay, so now we find everything. Then you can write A as U sigma V transpose. So now if we find U sigma V, and that's our singular value decomposition. It takes some time, but it's definitely accessible. So make sure everyone knows how to do it. Yeah. We have like 8. Any question for this? In the problem set of this week, there are a few more examples to find the SVD for a matrix. So maybe after this week you can see the solution. So make sure to do some practice on that and compare your result with the solution. Yeah, but so this is a problem set. Let me just point out let's just quickly go through, because I already have a solution here. And let's go through question 5 here as another example. This is because it's someplace slightly different with the example we just go through before. That one is very kind of the easiest one. So let's consider the other one. This one is also a 2 by 3 matrix A. So we want to find the SVD, singular value decomposition of A. Okay. So first we find the singular values of A. The singular values of A just the square root of the eigenvalues of A transpose A. So we first write down A transpose A, which is that. Then we find the eigenvalues of A transpose A. Then we do a bunch of calculations we write here. So this is slightly different with the first example, because from here we can see lambda 1 equal to 18, lambda 2 equal to 0, lambda 3 equal to 0, which means the rank of A, the rank of A is just 1, because we only have one positive eigen values here. Yeah, and the singular value of A, singular value of A is just sigma 1, take sigma 2, sigma 3, they are 0, sigma 1 is 3 times root 2, okay? Yeah, so we know the eigenvalues. Eigenvalues is always the easiest part. So the rank of A is 1, okay, as we said, just 1. So find the singular value decomposition of A. So we already know the 3 eigenvalues. So let's find the orthonormal basis for the eigenspace for each of them. So for lambda equal to 18, yeah. So we need to find the base of for the known space of this, right? So this is equal to that, and which is a row similar to that. And I mean, this is kind of easy. You can find the basis is this V1. This one is okay. This one is not difficult. Yeah, and then we need to find the eigenspace corresponding to lambda equal to 0. But lambda equal to 0 has algebraic multiplicity 2 because this is lambda square here, right? So let's find the known space, the basis for the known space of this. So lambda equal to 0, so it's just A transpose A, and it's row similar to this one. So you have 2 rows, all 0. In this case, which means in this space, eigenspace, you have 2 bases. You have 2 bases, right? In the first example, like for each eigenvalue, its eigenspace, the basis for that is there's only one basis, or one basis. But now this one means we have 2 of them. So by using back substitution, you can find, okay, you need these 2 bases to span the known space of this. They are not unit vectors. They are not orthogonal. But we need orthonormal basis, so we need to do a bit more work by applying the Gram-Schmidt algorithm. That's why I talk about this example. Is in some cases you may need, if some eigenspace, there are more than one basis, and the basis you find, if you are lucky, maybe you will get orthonormal basis directly, but normally the bases you have, they are not orthogonal. So you need to use Gram-Schmidt algorithm to use these 2 bases to get 2 new bases, but they are orthogonal. And how to do that? Just use this algorithm. Yeah. So you get so now you just keep one of them, and you find another one which is orthogonal to the one you keep. So you can see, So the first element is still be 101. We just keep it. Okay, and the second one, we use this algorithm to find the second one. This is the second one. This is the first one. Now these 2 are orthogonal, but Gram-Schmidt's algorithm does not produce the unit vector directly. So you need to just normalize it. So you just normalize it. I mean, the normalization is easy. You just get 2. After normalization, you get 2 orthonormal bases. Yeah, that's a slightly tricky part. So then you put them together, you get V. Okay, now we have V1, V2, V3. You put them together, you get a V. Yeah, and then to obtain U, this one is also slightly different. So U, because R is equal to 1, so we only know U1 directly from this formula. We'll get U1, okay? And U2 and U3, they are the base, orthonormal basis for the known space of A transpose. Now we need to do a little bit more job to find A U2, U3. But that's also okay, easy. Just what's A transpose? A transpose just that. And the basis for And the basis for the known space of air transport, you can just use back substitution. You can see that's that. Yeah, that's just that. Yeah, because U1 and U2 that's enough, right? Because U is a 2 by 2 matrix. Yeah, that's enough. So we get U1 is here. U2 is we need to do a little bit more job find U2. Then that's U. And sigma is always easy. Sigma just once you find the eigenvalues, you find the sigma. So then you put them together. Put them together, you find a singular value decomposition. So this is a question 5, and also okay. The last one says find the orthonormal basis for this, and this. That's row known, column known of this. They are just then they just the use of this theorem. Yeah, this theorem directly tells you what is the basis of this is this. Okay, yeah, that's all for today. Yeah. Any questions? Yeah. Yeah, do some practice for this SVD. Yeah, it's and then you will get more familiar with it. Yeah. Okay. Yeah, that's all for today. Thank you, everyone. Oh, sorry. Let me connect it.